So thank you for joining us in our study of the Unit 5, Topic 1, AP Chemistry Rescue. So let's see our system here. What is a chemical reaction rate? The rate of the reaction we'll know if we imagine watching a candle burning. So some candles will burn quickly, others slowly. In chemistry, we need to quantify this speed. So that's what the reaction rate measures. So reaction rate is a change in the concentration of a reactant or product per unit time. How much the reactant decreases or the product increases per unit time. So I can say it's change in concentration per change in time. That's the delta of concentration or the change of the concentration. That's the concentration between brackets over delta T, which is the change in the time. What was the time at the beginning and at the end? What was the concentration at the beginning and the end? Now let's see an interactive rate visualization. I will see how the concentration changes over time and see the rate calculation in action. I will see first the reaction where there is reactant A and product B. Reactant A is disappearing and product B is forming. So the rate is the change in the concentration per time. So let's see. First, I have decreased from 2 molars or 2 mole per liter into 1.8 mole per liter, while the concentration of the product was 0 and it is increasing. So the concentration of the reactant is decreasing and the concentration of the product is increasing, and it depends on the time. So let's see, this is the autoplay. It's slow. So this one is decreasing and this one is increasing. We can make it faster. Okay. So this is faster rate or slow rate. How fast this is decreasing or how slow it is decreasing. It can be decreasing in a very small rate or in a very fast rate, like we can see. So let's reset it and then make it in slow rate. So the rate by which this one is decreasing would be small and is also increasing in a small rate, or we can make it in a fast rate. How fast this is decreasing and this is increasing, this is the rate of the reaction. So what you are seeing, let's make it from the beginning and see. Here there is second 0. This is starting point. The reactant is at its maximum concentration, beaker is full, and product B is 0, concentration, beaker is still empty. Rate is about to be highest because A is at maximum. So the rate is still nothing happening, but then if I step one forward step, the reactant is 1.81, dropping quickly. Notice the blue level falling and product P 0.19, rising quickly, green level climbing. The rate is 0.181 molar per second. So every second, 0.181 molar is decreasing from the reactant and increasing in the product. The rate at the beginning is very fast because there is a lot of A remaining. This we call the reaction is in high gear, plenty of A molecules to convert to P. Then after that, it's still decreasing, it's still in the high gear, decreasing, and A is decreasing and B is increasing. The A is dropping quickly and the B is rising quickly. Now I almost have very little from the reactant. It's disappearing and product is forming. This is like a campfire burning down. There is less fuel, means lower burning. So because the reactant will be less, then the possibility of the reaction happening becomes less. There is less particles to collide with each other and make the reaction. About half the blue is gone and half the green is formed. So the rate now is 0.110. It's slowing down because A is getting used up. Until almost all the reactant is decreasing, the reaction here is out of steam, fewer A molecules left to react. The A is mostly consumed and the B is nearly complete. The A is mostly consumed, a very low blue level, and the B is almost full. More. Here, this is like the last embers of a fire. Very little left to burn in the A, and the B is almost full. Almost all A gone, tiny, very blue. tiny blue level, and B, green level almost full. I will move forward more until I have nothing left over. Then all the reactant will be changed into B. How fast this has happened is the rate of the reaction. So if we started this from the beginning, we can see also the reset and see the curve here. So this is the beginning. The concentration of the product is 0 and it keeps increasing, and then suddenly it becomes constant value because all product can be formed is formed, and the reactance also is decreasing from 2 until it reaches a very low amount, then becomes constant. If you want to find the rate of the reaction, we said that it is the product or the reactant over the time. So here in this curve, it will be the concentration over time. So this is the slope. If you want to make the slope of the beginning, you will see that it is the product concentration over time. So we can make a line, and see the rate. So this one over, oh, this one is the slope of at the beginning, and we'll see that it is a big slope because there is a high rate of the reaction. In the middle time slope, it will be less because, as we said, the reactance is less. That's why the reactance, the product's concentration over the time is a less slope, and at the end, it becomes very small slope because the rate is very small. So the blue curve is the reactance concentration decreasing over time. The green curve is the product concentration increasing over time. The curve shape, both curves are exponential steeps at first, then leveling off. First steeping and become very steep, and then it's leveling off. This is the same, it's very steep, and then leveling off. Why this shape matters? Because early time there is a lot of A molecules, fast reaction, then the slope is steep, as we said. This is the early time slope. The slope is steep here because steep downward slope for the blue line A disappearing fast, and high concentration of A means molecules available to react is high. Fast reaction rate because collision frequency is high. Slope is equal to negative 0.164 moles per second. The negative sign shows that A is decreasing. Think that steep hill, fast change, high rate. But if I make a little bit middle time slope, I can see that the middle time slope here, there is fewer A molecules than before, so moderate downward slope. For the blue line, A disappearing slower, and medium concentration of A. Half the original is almost remaining only. Medium reaction rate, fewer molecules to collide, the slope will become 0.074 moles per second. At the beginning it was 0.164, so it was more. Now it's less, and then finally it will be very small slope. Why is that? A very gentle slope here because the blue line has a small slope because the low concentration of A most has been consumed, a low slow reaction rate because very few A molecules are left, and that's why there is a very small slope as the rate of the reaction is very small because it's approaching flat. So a gentle hill is equal to slow change, so a low rate. We can make another analogy by step-by-step bathtub draining. What we measure water level, gallons, it decreases over time. So the rate of the calculation equal to final level of water minus the initial level. What's remaining in the final level in the water in the bathtub, and what was the initial level divided by time. So at the beginning, there was 50 gallons inside the bathtub. At the end, there is 10. So 10 minus 50 is equal to 40 divided by 20 minutes. This means that it is negative 2. So the rate has to be negative of this value so that the rate comes as positive. Remember this, the rate of the reaction has to be positive at the end. So I will say that the rate is 2 gallons of water is draining out from the bathtub per every minute. So it will take 20 minutes to finish 40 gallons of the water. The chemical reaction, for another example, what we measure is the concentration or the molarity, how it changes, reactant decrease, products increase. Rate calculation, rate is equal to final A minus initial A divided by time. Rate is equal to 1 mole minus 3 mole. For example, it was 3 mole at the beginning and become 1 mole at the end, divided by 20. So rate is equal to negative 0.1 molar per second, meaning the concentration of A decreases at 0.1 molar per second. So what will be the units of the rate of the reaction is equal to the units of the concentration divided by the units of time. Unit of concentration is either molarity or mole per liter, and unit of time is seconds, sometimes minute or hours, but we'll change back to the seconds. If it's a very short, very slower action, it will be by minutes or hours. The rate units are always concentration over time. In AP chemistry, this is always molarity per second or mole per liter per second. In the next video, we'll talk about instantaneous and average rate.